Okay, our curve here, well, let's you know, we didn't really start here. Let's start down here. Okay, we assume a continuous flow of $6,000 per year into our account. Then we ask ourselves how much money flows in during a given time interval. Because in order to calculate how much the money flowing into the account during any time interval from t to t plus delta t, we want to start with knowing how much money has flowed in. Then we want to ask ourselves, well, how long does it take, or how long does it have to accumulate? Okay, so we take a typical interval from t to t plus delta t. In 1 year, then, at this continuous rate of flow, in 0.1 year, in a tenth of a year, how much money would flow in? Well, in a tenth of a year, we'd multiply a tenth of a year by the $6,000 per year to get $600. It's clear that if $6,000 flows continuously at a uniform rate into the account for a tenth of a year, we're going to end up get we're going to have $600 during that time interval. Okay, so in a time interval delta t, if the time interval instead of 0.1 year is delta t, which could be anything, could be half a year, it could be 12 seconds. Okay, if I tell you what delta t is, knowing that money flows in at $6,000 per year, then you're going to be able to tell me how much money flows in. So what's the general expression in terms of delta t for how much money flows in during that time interval? Well, $6,000 a year times delta t. Same reasoning we used up here. If we multiply a 0.1 year time interval by $6,000, that means, well, if we used a different time interval, we'd multiply that time interval times $6,000 per year. Okay, and if the time interval is delta t, that's what we multiply by $6,000 per year. So that's how much it's going to be worth. Okay, well, then we ask how much that amount is going to be worth at t equals 20 years. Okay, well, people did a good job of understanding that, okay, well, that depends on just where this thing is. Here, here, here. How close to the 20 years is it? And people then did quite a good job of figuring out that, okay, well, let's see. That means how long does it have to grow? Well, yeah, people figured it out real well. I don't know if somebody said t minus 20 years or if I just wrote it backwards, but it'd be 20 years minus t, wouldn't it? And of course, that's the way I wrote it here. I think maybe I was just being careless here. In class, I asked, okay, well, from 5 years, how long does it have to grow? If t is 5 years, how long does it have to grow? I said, well, 15. I said, okay, if t is 12 years, how long does it have to grow? Well, 8 years. What did you do? We subtracted the number from 20. So it's going to be 20 minus t years to grow. Being a little careless with the units here. We get the idea. The time it has to grow is 20 minus t, or t is in years and 20 is years. So what will the value be? If this amount grows for this long, how much are you going to have? Well, it's going to be this amount, which is, I'll just write as 6,000 t times e to the 0.04 times the number of years you still have to grow, which is 20 minus t. Now, that's how much we would have for a typical interval. T is just the time at the beginning of the interval. So the total value, and this would be a total approximate value. Class was better at using the word approximate than I am, and I try to emphasize it, okay? So everybody's doing real well, but total approximate value would then be the sum of all such intervals. It would be this sum of this expression over our partition of the t interval from 0 to 20. In other words, we take the interval from 0 to 20, we partition it into intervals, let's say, of width delta t. We could use other partitions, but for simplicity, let's think of this, okay? So we partition this interval into smaller intervals of length delta t, and for each interval we have some starting time t. So this t is going to change from one interval to the next, but everything else is going to be the same. Well, we sum all those up and we get the approximate amount. That would give us approximate amount for every interval, and we'd add them up. Okay? Now, as delta t approaches 0, because of course we're going to want to get an integral here, and we understand that an integral occurs in the limit as your subdivision length approaches 0. So subdivision length is delta t. As delta t approaches 0, we get more and more of these. We have less and less error due to the linear approximation we're using on each interval. And the result is that the sum approaches the exact value, and that exact value is this integral. The integral is, well, it's with respect to t. It's like the delta t by some kind of magic becomes a dt. And depending on the level of a calculus course, we spend more time understanding exactly how this limit works. In an applied calculus course, which is what this is, we don't belabor that, but if you're looking at this and you have a more advanced calculus course, you should understand how this limit approaches this integral. In any case, bottom line is the delta t becomes a dt. If you just want to get the integral, the delta t becomes a dt. The rest of the expression stays the way it is, and the integral has limits that are equal to the endpoints of your interval, of your t interval, the t interval that you partition. That would be this t interval. And we understand now how this sum represents a sum of areas. And as delta t approaches 0, how the sum more and more closely approximates the actual area under the curve given by this quantity, or given by this rate. So there it is. There's our integral. This is a very easy integral. Everybody should do it. And I even start you on it, although I don't think it's necessary. Just let u equal this exponent. du is then going to be negative 0.04, and so forth. And it's, I say 0.04, etc. Careless again, 0.04 dt. And then you proceed with the rest of the details of the u substitution, and you get a very easy result.